In part 5 of our lesson on graphs of secant and cosecant, you will learn how to write the equation for a function given its graph. In this example, we have to determine two possible equations for the given graph, one secant and one cosecant. Let's start by writing the standard form for these equations. We know the secant one will look like y equals a secant of the quantity b times x minus c plus d, and the cosecant will look like y equals a cosecant of the quantity b times x minus c plus d. Our job is to find a, b, c, and d. Now, when we look at this graph and we want to find a, what you can do physically looking at the graph is find the vertical center of the graph. So this upper value is here at 1. This lower value is here at -3. Halfway between -3 and +1 is -1. So this is sort of the vertical center of the graph. And you can see that the distance from this center line out to the minimum here is a distance of 2, or from the center line here down to this max is also a distance of 2. So we know that the absolute value of a is 2. If you're not comfortable getting it from the graph that way, or you just want another way to check, you can do this calculation where you say the absolute value of a is going to be 1/2 of that upper value, 1, minus that lower value, -3. So it will be 1/2 of 4, which is 2. So the vertical stretch or compression is a factor of 2, which means it is a vertical stretch. When we compare this graph to the graph of unaltered secant, it's not flipped. Which means a has to be positive, so a will be +2. We know that the period we can compute from the graph by subtracting the end minus the start. So the end value is here at pi, and the starting value is over here. So we need to figure out what that x value is. So if this is pi right here, then that means 1, 2, 3, 4, 5, 6. That means each of these dotted lines is going over by pi over 6. So this would be -1 pi over 6. So that means this is -2 pi over 6. Or we can write it as -pi over 3. So that means the period will be the subtraction of pi minus -pi over 3, which means we have 3 pi over 3 plus pi over 3, and we get 4 pi over 3. Now, when we're using letter B to calculate the period, we know we have to put 2 pi over b, and now we'll cross multiply. This 3 is going to come up to the left-hand side, so this will become 6 pi. this b will cross multiply up while the 4 pi will cross multiply down. And we see that we get that b is equal to 3/2. To get letter C, we know we have to look at the phase shift of the graph. And to get the phase shift, we have to start from the unaltered graph of secant and look at what's happening on the y-axis. And we see that on the y-axis of unaltered secant is this minimum point, and on our graph, right there on the y-axis, that minimum point is still there. So for secant, there's been no phase shift, which means C is equal to 0. Next, we'll look at the vertical shift. And for that, we can use that center line that we made earlier when we were looking at the vertical stretch. We know that for unaltered secant, the center line of the graph should be on the x-axis, and instead this has shifted down by 1. So that means the vertical shift is down by 1, which tells us that d is equal to -1. Now we're ready to write our secant function. So we've got y is equal to, well, we said a is going to equal 2 times the secant of the quantity. B, coming from the period, will be the same for both graphs, 3/2 times the quantity x minus. Now, the phase shift for secant was that there is none, so I'm going to take that minus sign back out. And then the vertical shift of the graph is down by 1, so there is our secant function. Now let's do the cosecant function. We're going to get y is equal to, for cosecant, again, this graph is not flipped, so a has to be positive, so a is going to equal 2 times the cosecant of the quantity. The period is the same, since the starting and ending values are the same. Now that means b will be the same, so 3/2. The phase shift we need to look at for cosecant. Let's look at the graph of the unaltered cosecant function. Now, looking at the y-axis of the unaltered cosecant function, we see that what we expect to be there is the first vertical asymptote. And instead, on our graph, that first vertical asymptote shifted to the left by pi/3. So for cosecant, we do have a phase shift. It is pi/3 left. Now, because it's to the left, that means C has to be -pi/3. And remember, that means when we write it in our function equation, we're going to put x plus pi/3. So when we come back up here to our function equation, we write x plus pi/3. And the vertical shift is the same for secant and cosecant because that center line of the graph has moved down by 1. So this is also a minus 1. And there's our equation if it's cosecant. In this example, we have to determine two possible equations for the given graph, one secant and one cosecant. So we'll start by writing down the standard forms for the function equations, and this time maybe we'll start by doing the cosecant first. So we have y is equal to a times the cosecant of the quantity b times x minus c plus d. And then for the secant, we'll have y equals a times the secant of the quantity b times x minus c plus d. It's CYU time, so pause the video, work the example on your own, then restart the video to check your answer. Okay, let's see how you did. And now we'll go about finding A, B, C, and D. To find absolute value of A, we can do a computation where we do 1/2 of the upper value, which is 2, minus the lower value, which is 0. Half of 2 is equal to 1. Now, another way that you could have seen that the absolute value of A was going to be 1 is to find the vertical center of the graph. We know that the vertical center is going to be between 0 and 2, which means it's going to be 1. So this is our center line. And you can see that from the center line out to the graph is a distance of 1 in both cases. So that tells us that the absolute value of A is 1, and so there is no vertical stretch or compression. Now in this case, we can see that this graph has definitely been flipped. When we compare to the unaltered cosecant graph, normally the upper branch of the function comes first and then the lower branch comes second, and instead it has been flipped over. So because this has been flipped, that means A has to be negative, so that means A is equal to -1. Next, we can look at the period of the graph, and we have to subtract the ending value, which we see here is pi, minus the starting value, which we need to figure out. So since this is pi, that means each dotted line is going over by pi. So then the starting value is going to be -1 pi, -2, -3, -4, -5, -6, -7 pi. So this becomes pi plus 7 pi, which is 8 pi. Now when we use letter B to compute the period, we know we have to do 2 pi over B. So we need to take the B and cross multiply it up to the right-hand side. We're going to take the 8 pi and cross multiply it down, so the left-hand side becomes 2 pi over 8 pi, which means that B is equal to 1/4. Next, we'll look at phase shift. And we'll start with our cosecant function. if we look at the unaltered graph of cosecant, we know that at the y-axis, we expect to see the first vertical asymptote of the function. Now remember, this function has been flipped over, so when you're thinking of the first vertical asymptote, this is still the first vertical asymptote. It's just that the function has been flipped over. So this first vertical asymptote here has gone to the left by 7 pi, which means c has to be negative 7 pi, which means that what we write is x plus 7 pi. Then finally, we will have the vertical shift, and for that, we can use that center line on the graph, and we can see that when we look at the unaltered graph of cosecant and look at what's happening on the x-axis, that's where that center line should be, but instead it has moved up by 1. So then that means the vertical shift is up 1, which tells us that d has to equal positive 1. So now we are ready to write our cosecant function. We're going to have y is equal to, a is negative 1, so we can just put negative cosecant of the quantity. B is 1/4 times x minus, now remember c was negative, so we're writing x plus 7 pi. And the vertical shift was up by 1. So there's our cosecant function. Now to write our secant function, we've got y equals, and again, we're going to use a flipped version of secant. So a is negative 1, so we'll write negative secant of the quantity. B is 1/4 because the period is the same since the starting and ending points are the same. X minus. Now we need to look at the phase shift for secant. So when we look at the unaltered graph of secant and we find out what should be happening at the y-axis is that first minimum point. Now you have to be careful here because we're using the flipped version of secant, then this becomes the first minimum point that turned into a maximum when it got flipped. So that means the phase shift for this negative secant function is that it is to the left by whatever this x value is, and this looks like it is 1, 2, 3, 4, 5. So this is negative 5 pi for this x value. So that means the phase shift is to the left by 5 pi. So c is negative 5 pi, which means we have to write x plus 5 pi in our function. So we come up here to the function and write x plus 5 pi. The only thing left to do is the vertical shift, and the vertical shift is the same as it was for cosecant, which is up by 1. We can see that center line moved up by 1. So here's our function equation if it is a secant.